Section 4.2 is area. All right, so let's just reproduce that quickly here. So we have the function y equals x squared plus 1, and we're going from 0 to 5. And we want to approximate this area. And the way we did it, the way we can do it, is we're going to build, let's make life a little bit easier on ourselves. Let's build 5 rectangles. Why would making 5 rectangles be a little bit easier? Each one would have a width of 1. 1, 2, 3, 4, 5. So we're going to build 5 rectangles. And when we build our rectangles, on each interval, we're always going to use the left-hand point to find the height. Do you always have to use the left-hand point? No. That's right. So this is called the left-hand approximation. If we chose to always use the right-hand point, we would call it the right-hand approximation. Notice when I do the left-hand approximation for this problem, is my answer going to be too big or too small? It's going to be too small because I'm missing like area here and area here. If I were to do the right-hand approximation for this problem, my answer would be a little bit too big. All right, so let's just see what we get here. Area would be, generally what we do first is we calculate something known as delta x. And delta x is the width of each rectangle. So in this case, how wide is each rectangle? 1. Because it would be, you'll see this formula, b minus a over n. What's b? Nope. What are a and b? A is 0 and b is 5. So a and b is the interval that you're working on. In this case, we're working on 0 to 5. And what's n? The number of rectangles. So we would write delta x equals 1. The width of each rectangle is 1. All right, so our area would be approximately, I would take the width of the rectangle, which is 1, times the height of the first rectangle. How tall is the first rectangle? Not 2. 1, because I plug 0 in. I always plug in the left-hand endpoint. If I plug 0 in, 0 squared plus 1 is 1. Plus, the second rectangle has a height of 1. I'm sorry, a width of 1. Times, how tall is it? Now I plug 1 in, right, because this is 1, 2, 3, 4. That's 2. Plus, the third rectangle is 1 by, let's see, third rectangle, 1, 2, 3. How tall is the third rectangle? Not 7. Not 10. For the third rectangle, what number do I plug in? I plug in 2. If I plug in 2, I got 5. Plus, rectangle number 4 is 1 by 10, because now I plug in 3. Plus, the last rectangle is 1 by 17. So we add those up. 17, 27, 32, 34, 35. So our answer would be the area is approximately 35. But we would know that that answer is too small for this problem. Questions on that? What if I asked you to build 10 rectangles? Could you build 10 rectangles? You could? Okay, so let's do 10. So if n is 10, what would delta x be? It would be how much? 1/2, because it would be b minus a over n. That's going to be 5 minus 0 over 10. That's going to be 1/2. Okay, so now my area would be, what's the height of the first rectangle? 1. Why is the height of the first rectangle 1? You plug in 0. So it's going to be 1, and the width is a half. Plus, how tall is the second rectangle? How much? And how'd you get 1.25? You plug 1/2 in, because now, back up in our picture here, we're going to have 0, a half, 1, 3/2, so on and so forth. Our second rectangle would look like this, where we would have to plug in a half. So we would have a half squared plus 1, that's 1.25, times a half. Plus, how about the third rectangle? What number do you plug in for the third rectangle? You plug in 1. And when you plug in 1, you get 2 times a half. Plus, this looks pretty tedious, doesn't it? What number do you plug in for the next rectangle? 1.5. And then the rectangle after that, you're going to plug in 2. And then the one after that, you're going to plug in 2.5. So you're going to keep increasing by a half each and every time. And when are you going to stop? Nope. You won't actually get to 5. What will be the last one that you use? 4.5 will be the last one that you use, right? Because on the last rectangle is going to look like this. You always plug in the left-hand number. So the last number we would plug in would be 4.5. So we would keep going. I'm not going to work it all out. The last one would be 4.5 squared plus 1 times a half. And we could grab our calculator and work it out. There's got to be a better way. I agree. There's got to be a better way. Could we do it? Sure, we could do it. It would take a while, wouldn't it? It'd be kind of a pain in the neck. But we could do it. What if I said, okay, now about 1,000 rectangles?
Yeah, no.
Could you do it?
Not that way.
In theory, you could. It might take you a week, but in theory, you could do it, right? But it wouldn't be much fun. Wouldn't be much fun at all. All right, so we got to come up with a better way. Many, many years ago, as the story goes, a teacher didn't prepare to teach. So what teachers do when they're not ready to teach their class is they give their students a quiz. It's a good trick. So the quiz given was, add that up. And this was back before the calculators were allowed in classes. One of the students was exceptionally clever and came up with the answer in just a matter of seconds. Huh?
Is that exclamation point thing?
No, that would be if I was multiplying. 1 times 2 times 3 times 4 times 100. That would be called 100 factorial. Anybody got an answer?
Well, I've been this way before. So if you look at the 99 and the 1, and it's 100. So you keep doing that one, and it's, well...
Okay, so what the really clever student did is the really clever student wrote the same thing down again, but wrote it backward. Like so. And then added them together. And what do you get when you add them together? You get 101 plus 101 plus 101. No, you actually get 100 of them, don't you? You were right the first time. You get 1, 2, 3, 4. You get 100 101s. So what's 101 times 100? Add 2 zeros. 10100. But that's not the right answer. Why not?
Because you divide it by 2.
Why do you divide it by 2?
Because you just multiply.
Because we have 2 of them, don't we? So if we want the final answer, we would take that and divide it by 2. It's 50-50, isn't it?
Yeah, sorry.
50-50.
Wait, no. Should be 550.
Oops, I got to start on this end, don't I? 50 10, bring down to 1, 0, bring down to 0, 50.
Why did you do that?
Why did I do what? Do long division? Just because I wanted to say that it really is 50-50. Right? You used your calculator. Did you get 50-50? Yeah. 50-50. We're all convinced it's 50-50. Who was the really clever student?
You?
No, I'm not that clever. It was not Einstein. It was not Newton either. It was a guy named Carl Friedrich Gauss. Gauss. All right, but the key is, notice if we want to add up 100 numbers, what did we have? We had 101. If we want to add up 100 numbers, we have 101 100 times, but then we have to divide it by 2. What's that?
Take n plus 1 times n divided by 2.
All right, so here's the general rule. If you want to add up a bunch of numbers, 1 plus 2 plus 3 plus 4, up to any given number n, there's a nice, easy way to do that. The formula is, notice when we wanted to add up to 100, we had 101, and then we had it 100 times, but then we had to divide it by 2. All right, so in fancy math symbols, you'll see this. I should have used I there. The sum from I equals 1 to n of I is n times n plus 1 over 2. So what does this symbol mean? The symbol that I wrote. It means summation. So this means you start at the number 1, you plug 1 in. And then you add, you plug in 2. And then you add, you plug in 3. So on and so forth. So for example, if I gave you the sum from I equals 1 to 4 of I, what would that mean? 1 plus 2 plus 3 plus 4. You plug in each number and then you add them together. How much is 1 plus 2 plus 3 plus 4? 10. What if I gave you the sum from I equals 1 to 600 of I? What would that mean to do? The easy way, it means 1 plus 2 plus 3 plus 4 all the way to 600, but you're right, the easy way to do it is, according to this formula, it's 600 times 601 divided by 2. So you see what we're developing here? We're developing shortcut ways for adding up a whole bunch of numbers. So in that area problem a minute ago, if I asked you to build 1,000 of them, and you told me, well, that wouldn't be very easy. If you have a technique like this for adding up a bunch of numbers, it would be a lot easier. So what's 600 times 601 divided by 2? How much? 180,300. All right, so we're going to have some formulas here in this section. The sum, I'll start writing them down. This one we already did. The sum from I equals 1 to n of I is n times n plus 1 over 2. There's a similar formula if you have I squared. So this would mean 1 squared plus 2 squared plus 3 squared all the way up to n squared. Anybody happen to know the formula for that one?
That same process. It's just you have to take the same thing and you have to flip it around again. So then you end up getting.
Would you just square it out?
Unfortunately, no, that doesn't work. So what would you do if you didn't know the answer to a formula? Number 1 would be derive it. Number 2 would be... It's probably in your book. Let's look in the book here. N times 2n plus 1 times n plus 1 all over 6. Okay, so there's the formulas that you need. They're on page 255 of your book.
It's the third one that's squared, right?
Third one. Yeah, the third one has squares in. Alright, so this one is n times n plus 1 times 2n plus 1 over 6. And I'm not going to show you how that one's derived. That one's more complicated to figure out. What you need to do is you need to know it and know how to use it. And the third one, I equals 1 to n of I cubed, is the first one squared. That's correct. So if you can remember the first one, you can remember the third one. Just square it. And you should be able to derive the middle one. That's correct. From those two. Okay, so how do we use this for the problem that we were doing? Excellent question. Oh, we need one more formula. What if I just have a number? Some number C. And I ask you, take the number C and do C plus C plus C over and over again. How much is that? Not C to the, but C times n. That would just be C times n. All right, so what does this have to do with the problem we were just doing? All right, so again, we want to approximate this area, the area under this curve, from 0 to 5. How many rectangles do we want to build? 10. Okay? So we're going to build n equals 10. Again, I would know that delta x is b minus a over n, which is going to be 1/2. All right, so my area is going to be approximately. What number do I plug in for my first rectangle? 0 to get the height. So that would be, I'm going to write it down, 0 squared plus 1 times 1/2. I think it helps if I write it as 0 squared plus 1 so you see where things are coming from. Plus, for the next rectangle, what number do I plug in? The second rectangle. The second rectangle I would plug in 1/2. So I would plug in 1/2 squared plus 1 and then multiply by 1/2. Plus, let's do one more. What number do I plug in for the third rectangle? I would plug in 1, correct? But I'm going to write 1 as an interesting way. I'm going to write it as 2 times 1/2. Why did I write it as 2 times 1/2? Because this first one was just 0, right? The next one was 1/2. And we keep adding a 1/2 each time, don't we? So we have 0, we have 1/2, we have 2 1/2s. The next one is going to be 3 times 1/2, so I'll write the next one in. 3 times 1/2 squared plus 1 times 1/2 plus, and we would end at 4 1/2 squared plus 1, wouldn't we? All right, so now what we need to do is we need to write this way. Write it as a summation. What do we do? All right, so notice the first one has 0 squared plus 1. if I'm starting at 1, how am I going to get 0 squared plus 1? And then the next one, I've got to have 1/2 squared plus 1. And the next one, I've got to have 2 times 1/2. The next one is 3 times 1/2. The next one is 4 times 1/2, 5 times 1/2, 6 times 1/2. It would be easier if we started at 0, I would agree. Unfortunately, these rules tell us we have to start at 1. If we're going to use these summation rules, we have to start at 1. Unfortunately. There's a way to get around that. We'll see that probably tomorrow. All right, here's what I'm going to write. I'm going to write I minus 1 over 2 squared plus 1 times 1/2. All right, so let's think about this. What happens when I plug in 1? What's 1 minus 1? 0. So that would give me 0 squared plus 1. That would be the first one, wouldn't it? Now what happens when I plug in 2? What's 2 minus 1? 1. So that's going to be 1/2 squared. That would give me the 1/2 squared, wouldn't it? Plug in 3, what do you get? 2 times 1/2. So 2 over 2, 2 times 1/2 squared. The next one would be plug in 4. 4 minus 1 is 3. 3/2 squared. All right. Now what? Okay, I'm going to do a little algebra. This is the sum from I equals 1 to 10 of 1/4 times I minus 1 squared plus 1 times 1/2. Tell me what I did there.
You broke it up, and squared the bottom and moved it.
All I did is I squared the bottom, didn't I? 2 squared is 4. 2 squared is 4, and it stayed on bottom. Now I'm going to take this I minus 1 squared, and I'm going to FOIL it out. All right, so this is going to be the sum. I equals 1 to 10. I still have the 1/4. And then I'm going to have I squared minus 2I plus 1. Correct? Plus 1. And then that's still all times 1/2. Looks ugly. We're getting there though. All right, this is the sum, I equals 1 to 10, of 1/4 I squared minus 1/2 I plus 1/4 plus 1, all times 1/2. What did I do there? Distributed the 1/4, and now I'm going to distribute the 1/2 through. So I have the sum from I equals 1 to 10. 1/8 I squared minus 1/4 I. Well, what's 1/4 plus 1? 1/4 plus 1 is 5/4, and then I take 5/4 multiplied by 1/2, I get 5/8. All right, now I'm almost ready. I'm almost done. Now I'm ready to use my formulas here. What happens when I add up a bunch of things with an I squared in it? I go back up to my formula here. My formula with the I squareds is n times n plus 1 times 2n plus 1 over 6. So this is going to be 1/8 times n is 10. So I'm going to have 10 times 11 times 21 over 6. Minus 1/4. Now I use my formula just for adding up all the i's. So that one's going to be n is 10, 10 plus 1 is 11 over 2. Finally, I have to add up 5/8 over and over again. That's just going to be 5/8 times 10. And there would be my answer. Let me see what that is. Grab my calculator. 1/8 times 10 times 11 times 21 divided by 6 minus 1/4 times 55 plus 50 over 8. I get 40.625. So at this point, I've probably convinced you that it would have been a whole heck of a lot easier to actually simply write it out 10 times and then grab my calculator and type it all up. That's probably what I've convinced you of, correct?
A little bit.
A little bit. Yeah. Probably would have been easier to just grab my calculator, type this all up, and see what I get, and see if I get 40.625.
But if n is something bigger than that, then it's not.
But if n is something bigger, or if you're more clever, you don't use the left-hand endpoint. Use the right-hand endpoint. So let me do this exact same problem over again using the right-hand endpoint. And we'll see why it's easier.
There's an inch in your back.
Yeah, I know. For a minute I was going to make it go all the way down to the axis, and then I remembered it wasn't supposed to. So, yeah, it's not a very good parabola, I agree. It's supposed to be a parabola. Ignore the left-hand side there. See, it looks just fine. All right, now what's the big advantage of using the right-hand endpoint? Again, let's use delta x equals, let's use n equals 10. So delta x is still going to be a half. And so our endpoints are going to be 1/2, 1, 3/2, 2. Got the same numbers here, so on and so forth. But what makes it easier?
You avoid the 0.
We avoid the 0. That's correct. So we're still going to have, let's see, for my first rectangle, what number am I going to plug in? I'm going to plug in a half. So my first rectangle is going to be a half squared plus 1. And that whole thing will get multiplied by a half still, won't it? For the width. So this is the height, that's the width. Plus, what's my second rectangle? What number do I plug in? Plug in 1. But again, I'm going to write it as 2 times a half. 2 times a half squared plus 1 all times a half. What number do I plug in for my third rectangle? Which I'm going to write as 3 times a half. Squared plus 1 all times a half. Plus, and I keep going, don't I? But look how this works out now when I write my summation. The sum from I equals 1 to 10. I need, what number do I plug in? I plug in 1/2, then 2 halves, then 3 halves, then 4 halves, then 5 halves, then 6 halves. So what do I plug in here? I over 2, because I plugged in 1/2, 2/2, 3/2. So I'm just going to have I over 2 squared plus 1. Times a half. Excellent. This is the height of the rectangle. I still need the width. So what did we avoid? What was the messy thing with this one?
I minus 1 over 2.
The I minus 1 over 2 was messy because we had to FOIL it out and we got a big expansion. If you use the right-hand endpoint on these, they come out much nicer.
But that's only when we're dealing with 0 is one of the endpoints, right?
Right, and we'll deal with what happens if you're not starting at 0. We'll deal with that. We won't have time for that. Okay, so this is going to be, let's see, it's going to be the sum from I equals 1 to 10. This is going to be I squared over 4, correct? But then I'm going to have to multiply this 1/2. So that's going to be 1/8 I cubed, I squared, plus 1/2. So I squared top and bottom there, and I distributed the 1/2 through. Now we can get to go directly to our formulas. This is 1/8. We use the I squared formula. That's n times n plus 1 times 2n plus 1 over 6. Plus, this one's going to be a half plus a half plus a half 10 times. What's a half plus a half plus a half 10 times? 5. 1/2 times 10, which is just 5. All right, so now I can grab my calculator. I got less to type up, which is nice. So I've got 1/8 times 10 times 11 times 21 divided by 6 plus 5. I get 53.125. How accurate is that answer?
The same.
It's probably pretty much the same.
It's too big now.
Right, before, notice we got 40.625, and that answer was too small. How did we know that answer was too small? Just by looking at our rectangles, right? We knew we had area underneath that we weren't covering. This time when I used the right-hand endpoints, I got 53.125. That answer is too big. So how do we find the right answer? Average them would give you a very accurate answer. That's correct. It wouldn't give you the exact answer, though. What else could we do? We could build more rectangles. Instead of just building 10, we could build 50. We could build 1,000. We could build 1,000,000 of them. Averaging them would probably... Well, the problem with averaging them is then you got to do the left and you got to do the right, and then you average them. I think it would be easier to just build more rectangles and only do the right-hand side. If you only have to do 4, you're right. You'll probably be just as quick to do 4 rectangles for each side. All right, so what we will do tomorrow is we'll talk about building a lot more rectangles. Like we'll do this exact same problem again, except we'll build 1,000 rectangles. And we'll see what the difference is. And then we'll talk about how do you build an infinite number of rectangles? How do you get the exact answer?